Neutron stars are the densest objects in the universe, with the mass of a star packed into a sphere the size of a city. They're formed when a massive star undergoes a supernova explosion, leaving behind a remnant core so dense that not even light can escape its gravitational pull. These extreme objects have fascinated scientists for decades, and one of the most intriguing aspects of neutron stars is what happens when two of them collide. Studying neutron star collisions is an extremely challenging task, as these events are rare and often occur in distant galaxies. Scientists have to rely on indirect detection methods, such as gravitational wave observatories and gamma-ray satellites, to capture evidence of these cosmic crashes. One of the biggest mysteries surrounding neutron star collisions is the exact mechanism by which they produce gamma-ray bursts, the most powerful explosions in the universe. Researchers have proposed various theories, but a consensus has yet to be reached. Another challenge is the fact that neutron star collisions are often shrouded in mystery, with many aspects of the process still unknown or poorly understood. For instance, scientists are still unsure of the exact role that magnetic fields play in these events. The lack of direct observational data makes it difficult to model and simulate neutron star collisions with high accuracy. To make matters even more complicated, neutron star collisions are thought to produce a wide range of electromagnetic signals, from radio waves to gamma rays, making it a daunting task to identify and interpret these signals. The fact that neutron star collisions are often accompanied by the emission of gravitational waves adds another layer of complexity to the study of these events. Despite these challenges, scientists are driven by the potential rewards of understanding neutron star collisions, which could reveal new insights into the fundamental laws of physics and the behavior of matter in extreme conditions. When neutron stars collide, they release an enormous amount of energy in the form of kinetic energy, heat, and radiation. This energy is so immense that it can create a black hole, or even a neutron star more massive than the original two. The material from the neutron stars is stretched and compressed in the direction of the collision, causing it to heat up and emit intense radiation. As the stars approach each other, their strong gravity begins to distort space-time around them, creating a region known as the gravitational well. The neutron star's strong gravity also creates a region known as the ergosphere, where the rotation of the stars creates a kind of gravitational drag. This ergosphere plays a crucial role in the merger process, as it helps to slow down the rotation of the neutron stars and convert their energy into heat and radiation. During the merger, the magnetic fields of the neutron stars become twisted and tangled, releasing a massive amount of energy in the form of electromagnetic radiation. This radiation is thought to be responsible for the gamma-ray bursts observed in neutron star collisions. As the neutron stars continue to collide, they begin to deform and eventually merge into a single, more massive object. This merger can produce a range of outcomes, including the formation of a black hole or a neutron star. The exact outcome depends on the mass and spin of the original neutron stars, as well as the details of the merger process itself. One of the most fascinating aspects of neutron star collisions is the creation of heavy elements, such as gold and uranium, through a process known as rapid neutron capture or R-process nucleosynthesis. These heavy elements are formed when the neutron-rich material from the neutron stars is propelled into space at incredible velocities, where it undergoes a series of rapid neutron capture reactions. This process can create elements that are found nowhere else in the universe, and are thought to be responsible for the creation of many of the heavy elements found on Earth. The detection of gravitational waves from neutron star collisions has also opened up a new window into the universe, allowing scientists to study these events in ways that were previously impossible. The most dramatic outcomes of a neutron star collision are those that produce a gamma-ray burst, or a powerful explosion that can be seen from millions of light years away. These bursts are thought to be responsible for the creation of the heavy elements found in the universe, and are a key area of research for scientists studying neutron star collisions. The detection of gravitational waves from these events has also allowed scientists to study the internal structure of neutron stars, and has provided new insights into the behavior of matter in extreme conditions. From the challenges of studying these events to the dramatic outcomes that they produce, neutron star collisions are a rich area of research that holds many secrets and mysteries waiting to be uncovered. Thanks for watching. If you have any thoughts on neutron star collisions, leave them in the comments below. And if you want to learn more about cosmic phenomena, be sure to check out my other videos on black holes, dark matter, and more.